Yeah. So what I was saying is that so at each k, you will have this matrix element Hij, and for each I, you have to take only its three nearest neighbors. And from the structure of the crystal, which is given, um, so you have to figure out what are the coordinates of the neighboring sites. So have you all been able to do that?
I actually did that, but I don't have sufficient argument for one of the things that comes up later. Here,
Like
like
what? You don't have an argument for exactly what?
like if you could go back to the Mardar book
Mm-hmm.
and scroll above, he solves for the s orbital, the Hamiltonian element.
Mm.
Here it's a one cross one problem,
Mm.
but even in that we can see there are these terms. One is the epsilon orbital, the other is some u term, and the next is the parameter t.
Mm.
Now, in our case, also we'll have these terms. In diagonal elements, we are ignoring these additional terms, especially the U part.
What is U in this case? The
He,
overlap, is it?
yeah, he has defined it as an integral above in the previous page.
What is his notation? Uh,
Uh,
okay, okay. This is the contribution from.
only the rth side thing.
This is no. This I believe is the contribution to the on-site energy from the neighboring atoms.
Yeah,
We have discussed this. So
what we
that is
usually
all
write as
clubbed into
JTB.
this epsilon p in the given problem.
But isn't the notation epsilon p means that it's the energy of pth orbital?
No, 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 no. Don't assume that. It's just, see, eventually you will get an on site energy. So the physical thing to remember is that that quote unquote on site energy has contributions from other atoms. In principle, all the other atoms in the crystal, but depend if you are really interested in a quantitative calculation, you can decide where to restrict that and how to evaluate that term. But in principle, it has contributions from all other atoms in the crystal. So that is that epsilon term. Um,
No, also we have to write the t and alpha pieces accordingly
right,
in
right. So
terms of
that
some
is the part
integrals.
I'm asking. So could you get those? See, they are similar terms, except yeah, except that here you have t, and in the overlap integral you have the alphas.
Yeah, and I am a bit confused as to what I have written because I have written based on somewhat my gut feeling and intuition.
No, no, this is precise. You don't have to go by your gut feeling. If you understand the notations, uh, everything precisely works out. So alphas are overlap integrals between a p orbital. Say, let's say the way they have given here in this problem. So this is SAB and this part is HAB. Okay.
Yeah.
Now, HAB is the hopping matrix element connecting a B site to its three nearest neighbor A sites. Now, first thing you have to ensure is that you understand the structure of the crystal very well, not just how it looks. That's okay, uh, but what are the lattice vectors and what are the two atoms that form the basis and what are their locations. So, for the sake of completeness, let me do that. Let me just find out a picture for the
It's
honeycomb.
there in chapter 1 in this book only.
Yeah, that's okay. I mean, I should have one here as well. Just give me a minute. Okay, now let us look at this. So here is the honeycomb lattice. So you can, so if these two are this red atom and blue atom, these two form the basis. And you can, let me mark these as well. So let's say I mark this as an A atom. This red atom is A atom, and I call this blue atom, the B atom. So, and then you have to choose the lattice constants, lattice vectors, the primitive lattice vectors. So you can choose this one as your A1. So let me write that. So let's see, this is A1. And I can either choose this one. Here you have a choice actually. Either choose this one or this. Equivalently, I can choose this one as my lattice vector. And the convention that is used in the problem is that rather than this one at 120 degrees, this one at 60 degrees is chosen as the second lattice vector. So let's call that A2. So A2 would be here to here. That's A2. Okay, so that's your crystal. And then what? Every A atom has three B neighbors. This one, and this one. And every B atom has three A neighbors. This one, and this one. If so, the lattice vector that is given, or the length of the lattice vector that is given to you, that is constant A as 2.46 angstrom, is this one. This is 2.46 angstrom. So if you take this as A, you can, from the geometry of this triangle, you can work out what this distance B is. B, suppose this is the distance between two atoms in the basis. This will turn out to be A over root 3. Let me check my notes. I think it is A over root 3. Yeah. So this much will be A over root 3. Now, when I want to write these terms, so now when I want to write these terms, Hij, for each I, so when I is an A sublattice, these are called sometimes, I mean, in the context of magnetism, these are called sublattice. So I'm using that term. We'll get familiar with that when we get to study of magnetism. So when I'm looking at the A sublattice atom, when I is a sublattice atom, I have to sum over its three nearest neighbor B sublattice atoms. And then this Hij K would be the corresponding hopping matrix element. Okay, the matrix element of the Hamiltonian in the p orbitals at these on these two atoms. But then it's a Fourier transform of that. So this is this H R J R I is the hopping term T. This is the matrix element of the Hamiltonian between those two P states. And then you have to take this factor e to the I k dot Ri minus Rj. All right. So then basically what you have to figure out is, given an atom which is A sublattice, what are the coordinates of the B sublattice atoms relative to that? Similarly, when I is the B sublattice atom, you have to check what are the coordinates of the three nearest neighbor A sublattice atoms relative to that. So that will give you this Ri minus Rj factors. So it turns out that, as I said, let me write somewhere on this. So this length is B, and you can show that B is equal to A over, how do I write that? Square root 3. That is from the geometry. And the 3 neighbors of A sublattice, that is 3 B neighbors, would be nearest neighbor of A would be, let me pull it up here.
Oh, so you are sharing your other screen, I think.
Oh, I'm sorry. So this is B, and B is square root of A, where A is this much. Now 3 nearest neighbors of this A atom here would be at, one will be at 0B. How do I pull this down? Anyway, so one at 0B, the other at minus A by 2 and minus B by 2. And the third one will be at A by 2 minus B by 2. Why did it stop sharing? Okay, so let me try to do it here. I have to come back to this. So this is how the crystal looks like. So let's say this is an A atom. This is a B atom. I have taken this as A1 and this AB. A, B, oh sorry, A, B, A, B. That's how it goes. So A, B, A. Okay, and so this is A1. This would be A2. So the first thing you have to write is what is A1 and what is A2. So A1 is given as this thing, and A2 is, let's see what it comes out to be. A by 2x plus B by 2 AY. Okay, and then the next thing you have to find is what is this separate operation. So that if that is B, then B is A over root 2. Okay, now what are the nearest neighbors of A? A has 3 nearest neighbors, this, and this, all belonging to the B sublattice. So what is the coordinate of this? What is the coordinate of that? What is the coordinate of it? So we suppose we say this is 0, the origin. So then this, so let me mark these as B1, B2, and B. So that's a bad choice, but you will get the same result because this is equivalent to this. So I could have taken this A and this B to be within the cell, but that's okay. So the nearest neighbors of A, this A, would be at 0B, which is this one, and this one will be at minus A by 2 minus B by 2, and this one will be at A by 2, B by 2, yeah, minus B by 2. So this A by 2 minus B by 2. So those are the nearest neighbors of A, and the nearest neighbors of B will be with respect to this. So if this is 0, 0, then this would come out to be 0 minus B minus B by 2. Then one is this, the other is this. So minus A by 2 B by 2, and the one on the right would be A by 2. So these are the coordinates of neighbors of nearest neighbors of B with respect to B, and these are the coordinates of the nearest neighbors of A with respect to A. So once you have that, you have those Ri minus Rj's that comes in the exponential e to the I k dot Ri minus Rj. And these Ri minus Rj are actual locations of the atoms. Okay. So if the lattice vector is R, the two atoms are sitting at R and R plus 0B. That's how we have chosen this cell over there. And these coordinates are taking care of these. So now all you have to do is, so H, I, J, K for any K. So K is some Kx, Ky. And so I have to take I to be, wants to be the A sublattice site, wants to be the B sublattice site. So when I is A sublattice, when I is on the B sublattice, the sum over J would go over the B sublattice sites and only the nearest neighbors. So then, and the integral H I J I R J or R J R I, whichever way I put it. So these are all T. So they are all T. So then this will be given by T times exponential. Now you will have 3 terms. This sum over J would give you 3 terms. And so you have to write those. So for example, let's say if I is on A, I have to look at the B nearest neighbor. So this would be X times 0 plus K1 times B, which is K over root 3 plus E to the I derivative Kx minus A by 2 plus Ky minus A plus. Okay. So now this term goes away. So this will give you the first term that they have given in the expression of f. And then if you manipulate these two terms, as you can see, the factors with ky are the same in both cases. So they will give you some exponential, and from these two you can get the cos kx a by 2 term. So that is your f. And the other orthogonal term will just be the complex conjugate of that. Is it clear now?
Yeah, this part was clear.
Which part is not clear yet?
I mean, the expression for t, the exact integral expression in terms of potential.
No. All you have to write there is that it's the integral. I mean, it's the matrix element of the full Hamiltonian between the p orbitals on two neighboring atoms. That's all. You don't have to evaluate anything. Just to show that you have understood what these quantities are physically. Right?
Yeah.
Okay, so let's now, but before getting back to the discussion of phonons, I mean, lattice vibrations, there's something else I wanted to ask. In fact, I wanted to ask Kaustuv in particular.
Yeah.
This is about the assignment 1. Let me see what I have those. So I have a general question and I have something particular for Kaustuv. So the general question is, many of you have plotted this. So I'm a little confused about what this part is, because there's no accompanying text. So I don't understand exactly what system you have taken, what is the size and so on. So what is this part, by the way?
There is nothing being shared, so I don't know.
Sorry, I didn't get that.
Are you sharing your screen right now?
Oh, I'm not sharing the screen. Okay. Yeah, here. I'm talking about this part.
Yeah, so shall I answer my?
You want to show something?
No, I just want to say that you are asking the reason for this kink sort of thing.
First, I want to understand which part is this in terms of the distance. I mean, which part of the physical system this is?
So this is the part where the length exceeds L by 2 up until L by root 2. Because if the size of the box is L and the box is a square one, so up till L by 2, everything is inside the box, the circular region. If we draw from R to R plus dr, so that strip of dr comes within the box up until L by 2. From L by 2 onwards, that strip, some of it goes outside, like in the box way. Although we have identified the edges, so it's inside, but on the lower region, sort of a thing.
So why should it drop like that? It is something I don't understand.
Because we are only taking the shortest distance between the atoms. So the ones that were there were already closer to the center.
No, but
any two atoms have only one distance
of course
between them. So once we exceed L by 2, there will be some atoms, if you do the periodic boundary condition, there will be some atoms which we have already, although the n, that is atoms per area, is constant, there will be some atoms which we have already considered. So those we will not consider once we go L/2. So
Yeah.
that is why.
No, no, no. I don't understand. Can you share your screen, any of you?
I can annotate and show you in this only. I mean,
Okay.
yeah. So if we have a box like this, can you see my drawing?
Mm-hmm.
And consider the particle to be here right now.
Mm-hmm.
Now, if we start drawing R plus dr strips, we'll get at some radius this, at some other radius something like this. I mean, this is just touching the box. I'm not drawing, I cannot draw it properly.
Mm-hmm.
Then after this, we'll get something like this. So up until this point, the radius is L/2.
Mm-hmm.
And that is this point, the kink, where the kink starts to happen, because what's happening is that if there were let me change if there were particles over here, I'm sorry, yeah, can you see them, the dots?
Mm-hmm.
So these particles were calculated at some radius less than L/2.
Mm-hmm.
Whereas when I start having the strips of higher than L/2, this region, the strip that is going above, this part of the strip is actually here, like something like this, because of the periodic boundary condition. And these particles were already counted, these particles were already counted when in the strip which was less than L/2. The only extra particles that we'll get in this strip are the ones sitting around here in the edges, in the corners actually. And since it was a uniform distribution up until this point, like this kink point, L/2 point, we were getting a constant line because we have divided by the radius in the y argument of the graph. So this uniform behavior was up until L/2. After that, we are not counting all particles because some of those particles are actually closer to the central particle and not that far. Like, is that?
Let's see. So when you take this radius, for example.
Yes.
So yeah, that is the other question I wanted to ask you. So what is this sort of grid, R grid, that you have taken? So in this example, this is what this is Kaustub's plot, right?
Yeah.
So what is your system size? What sets your length scale?
Yeah, I
What
should
is
have
your
written
system
that.
size?
It's in the
And
code
what is
L
your
equal
R
4.
grid size?
Yeah, so the length of the box is 4.
Length of the box is 4.
Yeah,
And
this is 4.
Okay.
And I am the step size is around 0.05.
0.05. So suppose you count particles between 0 and 0.05, then
Yeah,
you take the next
0.05 to 0.1.
0.05 to 0.01 and so on, right?
Yeah.
So when you take this, let's say, basically when you draw a circle like this, you would be counting particles between this line and another line, which is, let's say, 0.05 away from this, right?
Yes.
Only in that strip.
Yes.
Now, when you count particles in that strip, these particles are not relevant, right? Suppose you have a circle which is just touching these corners, right? So you are counting particles between that circle and another circle, which is just 0.05 or 0.005, whatever you are taken, dr
Yes.
out of
Yes.
that. So that annular region. So then that so I'll look at all these particles and then see whether what is the shortest distance between this particle and those particles.
Yeah.
So I don't discount anything.
No, you don't. But what is happening is that at a distance r, like for instance, when we go in this direction, this y direction from the central particle, after L by 2, we encounter those particles which are actually closer to like the region and less than L by 2 in the bottom part of the box. Like if this length were something like let's say 1.9, and I took the radius strip to be 2.1, I'll encounter this particle again, the particle sitting at 1.9.
I understand. Now let me.
And that I don't have to count.
No, that
because
is
the shortest distance is 1.9.
no. That is what you have to count. Simply because that is the meaning of periodic boundary condition. You are repeating your system periodically in all directions. So you have to, when you take this circle, which is let's say L by root 2 to something, that annular region. So that annular region will contain particles which are periodic repetitions of whatever you had inside your box.
Sir, actually, this was the thing of conflict we were talking to about earlier when we had to submit the assignment, because earlier we were considering that only periodic boundary conditions by a repetition of the box. But you pointed out that instead of that, we could consider it as a torus. And
No,
torus is different from a repeated box.
It is still a torus.
If it's a torus, then this particle actually, like if I could draw a torus, perhaps I am not good at drawing. Yeah. So my central particle would be somewhere around here, let's say, on the torus surface. And when I start drawing, and there is some particle over here, let's say. This is the farthest particle that can be, and this is L by root 2 distance away at the corners. So all the corners are mapped to here. And there is some particle here at some 1.9 distance, as we are saying. So when I start drawing these strips, and I'll draw some 1.9 radius strip, this will be enclosed in that. And I mean, similarly here, when I start drawing a 2.1 size strip, it will again enclose this. But then this particle will be counted twice.
Oh, well, once as the particle in the box, at other distance, it's a repetition of its.
Different. Yeah, I understand
so,
that.
Maybe I did not quite understand the previous time what exactly this point was, or what your problem was. But that's okay. I mean, whatever you have drawn up to L by 2 is perfectly correct. It depends. Beyond that, it depends on. Probably there was some.
So if what you're saying that we need to count this again here, then it'll just
get a constant
stretch off like this.
This will continue at 1.
Yeah, exactly.
So that is not the most important point. The more important point is that is particular about your plot, is that I see more structure in this at point 1 compared to larger filling fractions. Is that what you expect?
I think that is because of my particular data points, in the sense that the jagged behavior comes because it's not exactly uniform. Because like when we have less number of particles, it is difficult to make to look at it and say that it's a uniform distribution.
So your system size is 4 in terms of what sets your length scale?
I mean, it's an arbitrary unit. It's just 4, and with respect to that 4, I am defining other. So the particle size is something like 0.05 only.
Okay.
The same order of my step size. So, and that shouldn't matter, because it's the ratio that matters, the number of particles in the box.
Matters, yes. So you could take particle radius to be 1 and define your system size on that scale. So suppose you Now you have the data, you can do that and send to me. Suppose instead of plotting GR over that 2 pi r, if you plotted just the G of R, what would you get?
It usually goes as a straight line because it's just a, I mean, G of R by 2 pi r dr is a constant after some initial values.
G of R itself would also become a constant after some initial value. In fact, it would go to 1. If you just plotted G of R, it should go to 1 as your distance increases, R increases. So I want to see your just the plot of G of R, because I don't understand why the system at smaller filling fraction has more structure than the one at larger filling fraction, because the atoms or whatever the particles would start seeing each other when you have more of them. Then this local order would appear, not when you have few of them, in which case G of R should be more uniform. So you just plot G of R without dividing it by anything and send me the plot.
That was a straight line which was having a slope.
Well,
That G of R is actually a straight line which is having a slope. That was the graph. It did not become constant.
no, why should that be?
I think even there we are also considering the boundary part to be different as what you're saying right now.
So G of R is the number of particles that are in that annulus region. So
Right.
if the radius is larger, that means the area is larger. And since my number of particles per area is constant, therefore for a larger area, there should be larger number of particles. So as we
See,
increase
this is
radius,
what you have drawn, Shan. This is what
yes.
you have drawn. You have plotted G of R. So I see some structure in G of R, and that structure is more pronounced when you have larger filling fraction. This is what I'm talking about. And as you go to larger distances, it goes to 1. There is no straight.
Yeah. Actually, I have written here G of R, but I have divided it by the area, that is the annular area, because since n is constant, n is constant. Therefore, if my annular region is larger, and that is larger for larger r's.
Okay, that's a normalization. Okay, fine. So
that is
that
what we
you
are
have got this.
Yeah, I have actually divided by 2 pi r dr. I mean,
Okay,
delta.
fine, which you have not written. Okay, but then again, so that doesn't solve the question, answer the question that why in Kaustubh's plot there are more structures at smaller filling fraction. So what you have shown in your plot is what is expected physically. As you put more of these, the local structure develops. But here it is just the opposite. So that is something, Kaustubh, you should check.
All right, yeah.
So I think even here in Shine's plot, at I equals 0, about I equals 0, there is some structure,
Harshit,
but it's smooth inside.
Harshit,
Hello?
your audio is not very clear. I mean, there's a lot of noise.
Just 1 minute. Hello?
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 Okay, go ahead, but there's still a lot of noise. Go ahead, we'll see.
Yeah, I'm saying even in Cheyenne's plot, there is some structure near r equals 0, but that structure smoothens out. If you see the plot for n equals 0.5,
n equal to 0.5, yes.
yeah, for larger distances, the structure is smooth. I mean, this plot is very smooth as
No.
compared to n equals 0.1 and n equals 0.3. There's only a peak about r equals 0, and that is expected because, like, even if the filling fraction is large, there is a high chance that near a point, near any atom, there is another atom. And if you divide it, if you try to normalize it with 2 pi r, you should get a peak.
Yeah, that's exactly what I'm saying. That peak you expect a peak uh, close to 0, and basically at twice the, or at a distance which is equal to the diameter of the particles. But then that peak should be larger when you have larger filling fraction.
Okay, yeah.
That's what I'm
But
saying. But in
yeah,
Kostev's plot, it's just the opposite.
Kostev's
Actually,
plot
I've
didn't
also
have any
divided
peak.
by the filling fraction in the end.
Oh, don't do that and see what you get.
Okay. Otherwise, the constants won't match, right? Not all of, like, g of r by 2 pi r dr, if we don't divide by a filling fraction, they will go to different values.
Yeah, they will not converge to 1. We have to divide by n, then only it will go to 1 in the end.
What were the expressions? I have to check the expressions, how we defined things.
It was basically number of particles per area per filling fraction for a single R.
Yeah, there was a division by average n, right?
Yeah.
Mm-hmm.
So on dividing, we shouldn't get different peaks. Like,
So in Chan's plot, have you divided by that filling fraction over here? What exactly have you plotted? That quantity you have written P of
I
R?
have, for a single capital R, I have counted the number of particles in R and R plus dr annular region,
Mm-hmm.
and then I have divided by 2 pi r dr and n.
Okay. No, that peak has to be different, right? I mean, how can it be the same? Suppose you are at a very low filling fraction, then there is very little chance that there will be anything around any given particle. So you won't see that peak. On the other hand, as you increase your filling fraction, because these are hard spheres, there'll be some point at which, I mean, of course, the probability of finding other particles around a given particle will increase. Then you will reach a situation where they just tightly fit in the system that you have, the box that you have. So then, so the peak height has to keep increasing. And once you reach that situation, after that, of course, you can't put anything else, anything more. You have reached a saturation. So that's how it should go. I mean, just thinking about it physically. At very low density, there are no particles around a given particle. So G of R should almost be constant over the entire range of R. In fact, if you look at the plots in the book, this Chaikin and Lubinsky, figure 2.4.1, you'll see that. That's exactly what I asked you to sort of reproduce. I don't think they have divided this by 2 pi r. That's why, or at least they have not plotted the other part where G of R is 0 below 2. But the peak height increases as your filling fraction increases. So anyway, Kaustuv, you look at your results once more and see if that changes.
Yeah, sure.
Oops, sorry.
Sir, before you start, I would just ask if you could tell us the syllabus for the mid-sem exam.
No phonons. The lattice vibration part will not be there. Whatever we have done before that, the electronic structure, I mean the Drude model, Sommerfeld model, and the rest of it, the electronic structure part, that will be there. Okay, so let us get back to the discussion of lattice vibrations. I'll start from where we finished last time. So we were discussing one dimension, I mean, this lattice vibration in a one-dimensional crystal, sort of a model system. And what we got was, let me rewrite some of this and then we'll start from there. So we were looking at this one-dimensional crystal, and so let's say this started at r equal to 0, and then goes like this, and this is point A. And we wrote, I'll just quickly go through this. The harmonic energy when these atoms move was written as this was dk. And from which we wrote the equation of motion. So each of them has mass m. So if I write the equation of motion of the atom, which is initially at the position in A, we got an equation involving this K. Okay, and then what we did was we said we can apply periodic boundary condition because we don't want to deal with end atoms or surfaces. So that was written as U0 as N. N is the total number of atoms or total number of primitive cells in my crystal. And we look for solutions of the form UAA. Okay, so now you put that into that equation, so you will get something involving omega square. Some factors would cancel out. So eventually we will get So one will come from this, the other will come from that. And which was written as then we got an expression for omega, so that each we have omega, which is okay, the 2 will count. So that's what we got. And so what are the allowed values of k? You have to put this in, so you get into the I k n k as 1, which gives you k equal to 2 n times, let's call that n1, not to confuse with that n, where n1 is an integer. And because the periodicity, I mean, you will get capital in distinct k values. And this capital in distinct k values, I can take these to be, you see, they are exactly of the similar form as we got in case of the electronic problem. So I can choose k, this small k, the wave number, to be this range, closed integer. Okay, and then the real sort of the motion of the atoms would be so in general, so this would be a superposition of these things. So let's call it. Actually, k depends on n1, so k. So the real sort of motion would be given by this. The point I'm writing this, I'm trying to make is that, so what you have got is, so you have n atoms, and you have a solution which depends on 2 n constants. There are n a's and n b's. So capital 2 n constants. So the initial positions and velocities of all the particles would fix this constant. So you have got a complete solution of the problem. The motion of all the atoms if your initial conditions are known. All right. So this now, we draw analogy of the small oscillations that you have learned. So there are n atoms to move, so they should have n normal modes. So these n values of k. So at each k, you have a frequency, and there are capital N k values. So there are capital N frequencies. So you have these n frequencies give you the n normal modes of vibration of the atoms in the crystal. And then the other thing I said is that, so because of this structure, as k goes to 0, so this is another important point. As k goes to 0, so this frequency omega q goes as to some constant. It goes as k. This is the constant, k or k by 2. Now that 2 will cancel, so root over k by m. So this is linear in k. So as k goes to 0, and at k equal to 0, this is 0. So I just said that it's a consequence of the fact that the crystal is formed by breaking continuous translational symmetry of free space. So now what we'll do is we'll come back to this issue of, or let me just draw it here and generalize it.
The screen share stopped.
Oh, it stopped. Okay, so let me draw it here and then I'll add things to it. So here it would be linear. So if you sort of solve the whole thing, I mean, plot this omega k as a function of k. This is what it is. Firstly, this tells you that it's an even function. I mean, it better be because omega is a frequency. And then at small k, we found a linear relation. So that is that. This should be symmetric. Both sides are the same. So it is linear here, but then it flattens off, and these are the things that you get at this being equal to pi over a. Okay, so we'll come back to this. So now what we'll do is we'll generalize this to a 1D lattice with a basis. So suppose now we don't have just one atom in a primitive cell, but we have two atoms. So these atoms are sitting at Na, and then within that cell there is another atom which is sitting at Na plus D. That is this atom is sitting at Na plus D, and this is the unit cell of length. So this much is N plus 1, A, and D is much smaller than A by 2. So now we can think of the system as these atoms connected to these atoms by, let's say, a spring of constant K, and these two are connected by a spring of constant G. So then, so when this moves, and we then write the deviation from the lattice ideal lattice position of these atoms, which are at Na, to be U1 Na, and the deviation of these atoms to be U2 Na. So this is sort of the nth cell, nth unit cell, if I start counting from here, and motion of these atoms are given by U1 Na and these atoms are given by U2 Na. So if that is the situation, then you can write U harmonic Okay, that's because when these two atoms in the same cell, they are moving, so they stretch this K spring, so that gives this term. And where the G string spring is stretched, when there is a relative motion between this atom, which is U2Na, and this atom, which is U1Na plus 1. So that's it. So now you can, and we'll also make the simplified assumption that both these types of atoms have the same mass. I mean, otherwise things will get a little more complicated, but we won't gain too much in terms of insights. So they all have the same mass, which is m. And then what we'll do is we'll write down the equation of motion for these atoms and these atoms. So you can do that from here. I'll just write the equations. So which is and similarly this would give you so these are the two equations of motion that you get, and we now seek solutions of in this plane wave form, but now we have two types of atoms. So we'll write this as some epsilon 1 e to the I and this one as So while epsilon1 and epsilon2 are vectors, in this case they are one-dimensional vectors, but in general, when we generalize these to three-dimensional crystals, they will be three-dimensional vectors, which will, as we'll see, give you relative motion of the two atoms in the same primitive cell. So now, again, you just take these forms, put in these equations. So here you'll get m omega squared u1, similarly m omega squared u2. Some factors will cancel out. So if you do the algebra, I'll write down the two equations that you get in terms of epsilon1 and epsilon2. So can I erase this?
Yes, sir.
So you get these two equations, and then consider these as equations for epsilon1 and epsilon2, and you will have non-trivial solutions when the determinant of the coefficients is 0. So you put that to 0 with these entries. So what does that give you? So this will give you. No, did I make a mistake? Yeah, I made a mistake. Sorry. This has to be different. So this will be in omega squared minus. Yeah, that was a mistake. So, so you have. So these are just complex conjugates of each other. So that's the condition. So from here, what you can do is you can calculate omega. Again, I'll leave 2-3 steps in between, which you can fill out, and you will get omega squared. So you get two values of omega, and you also get so now what you can do is you take two values of omega and put in any of these equations. So you can, from there, you can calculate a ratio of epsilon 2 and epsilon 1. So you get two different ratios in two different cases, depending on which value of omega you take. And so these will turn out to be again, you can fill out the algebra, but this is what you get. Okay. So again, I mean, as before, we can argue that we apply periodic boundary conditions. With that, you will get the same set of values of k, and I can choose those values of k to be lying between minus pi by 2 and minus pi by a and pi by a. That is confined to the first bit also. Okay, now what? So it's interesting to look at two different limits. So let us see. We take these two different signs, that is two different values of omega, and we see how these frequencies go as omega as k either tends to 0 or k goes to pi over e. So I'm looking at this equation now. There are two values of omega square. If you take the minus sign, and I look at the small case, k going to 0. So again, simple. You take this, take the minus sign, you expand cos Ka for small values of Ka. And after some manipulation, you will get omega k So with this sign, minus sign, you again get an omega which goes as k linearly with k at small values of k. So 0. Exactly as we got in case of the monatomic one-dimensional crystal. If you take the plus sign and small k, you can do the same exercise, expand this, take the leading order term, you will get, writing here, yeah, that is right. So here you will get omega k or omega at k equal to 0 is and there will be some order k squared terms after this. So at k equal to 0, this is what you get. So now see what we have got. At each value of k, you are now getting two omegas from here. Now one branch goes linearly as k at k equal to 0. The other branch has a constant value, not 0 of course. at k equal to 0. So which will be somewhere here. Let's see. Even otherwise, at each k, you have two different values of omega. So you have two different branches. These are called two different branches of these lattice vibrations. And because you have two values of omega at each k, there are two n normal modes, which is understandable because now you have two n atoms if n is the number of primitive cells in your crystal. Each primitive cell has two atoms, so the total is 2n. So you should have 2n normal modes, and these are the 2n normal modes. The 2n values of omega at n values of k. Now, what happens at the boundaries? So we are now looking at the zone boundaries. Okay. If you take this branch, the minus sign, which one might be at minus or plus? No, I'm looking at the plus. Okay, so this one, again, you just put in the value here, you minus 1, and then you manipulate these terms. So this will give you omega A, that is omega phi A, is equal to and if you take the minus sign, that branch at A equal to pi by A, you can work this out easily. So I have another branch here, whose frequency is this much, 2k plus d over n here, and at the boundary it is 2k over n square root. So this is obviously larger. So this branch, the frequencies will go down and come here, something like this, and this branch starts from 0, linear here, then bends and comes here, and this value is this. So this much is 2k. This is n, and this is this branch is called the acoustic branch. This is called the acoustic branch because the dispersion of this branch at small k is linear in k, which is like sound waves, light waves, and photons, and so on. So that's because it's light sound waves, the dispersion is called the acoustic mode. In one-dimensional crystal, you will get one acoustic mode. In three-dimensional crystal, you will get three acoustic modes. And this branch is called the optical branch. This is called the optical branch because in actual three-dimensional crystals, particularly insulators, these branches play an important role in many optical properties of these materials. They respond to external electromagnetic fields and determine many optical properties of these materials. So these branches are called the optical branches. But just get familiar with these names. This branch is called the acoustic branch, and this branch is called the optical branch. So that's in a one-dimensional crystal, and then we have to understand what these epsilons are doing here. Okay. So again, the algebra is very simple. So I'll give you the ratios epsilon 2 over epsilon 1 in different situations for these two branches. And then we'll see how these modes look like in actual crystals. Oh, so remember we have got okay. So the first case we look at is when E is much less than, that is basically E to 0, that limit. So here, you will get epsilon 2 over epsilon 1 is -1 or +1 for the acoustic branch and -1 for the optical. So this plus or -1 is simple. You just put k equal to 0 and you get +1 or -1. Now, which one gives you +1? Which one gives you -1? For that, you have to look at the expression before this. In the expression of epsilon 2 and epsilon omega or their ratio involving omega square. So you have to make sure which omega you are taking. If you're taking the omega for the optical branch, you get a -1. If you take the omega for the acoustic branch, you get a +1. That's it. All right. The other situation one looks at is when A is at the zone boundary. And here, again, you will have epsilon 2 over epsilon 1. I mean, in that expression, again, you can put Ka equal to pi, and you will again get +1 for the acoustic and -1 for the optical. Now, this is fine. Now, what does this tell us and what do we understand from this? So what we can understand from this is that how these atoms move. You excite a particular mode. The other thing to realize is that, let us see how we wrote the solutions. Solutions were written as U1 So one thing to understand is that as you go from one cell to other cell, what changes here is this n. N goes to n plus 1. Now when n goes to n plus 1, you pick up a factor. So anyone, I can take anyone, u1 n plus 1 is pick up an additional phase, which is K. Now, if Ka happens to be 0, they are in the same phase. That is, all the primitive cells are in the same phase. If, on the other hand, Ka happens to be pi, then you pick up a minus sign. So this tells you that at least at the zone boundaries and at k equal to 0, how the vibrations in the lattice looks like. So I'll show you some figures here. All right. So here in this figure, 22 point whatever 11, we are looking at the k equal to 0 mode. So what we said right now is that if k equal to 0, then all the primitive cells are in the same phase. So so here again, notice that this is the K spring. So these two atoms are in the same cell, and these two atoms are in the same cell. Now, whatever this cell does, this cell will do exactly the same. Okay, so if the two atoms are moving in this direction, these two atoms would move exactly in the same direction. Now, what are these two atoms doing relative to each other? So we found, remember, that epsilon 2 by epsilon 1 is plus 1 for the acoustic mode. So if we are looking at the acoustic mode, then the two atoms are moving by the same amount in the same direction. So therefore, these two atoms does exactly the same thing. So if it moves this way, this also moves this way. And because at k equal to 0, each primitive cell has the same phase, these two atoms move by, exactly in phase with these two, and so on. So the entire crystal is moving to the right. Or if it oscillates, then the entire crystal is oscillating. All the primitive cells are oscillating in phase about the mean position. And that's exactly the k equal to 0 mode, and that doesn't cost energy simply because space is homogeneous. So that is the k equal to 0 mode. Or generally, the small k modes are called long wavelength modes. When k is 0, of course, the wavelength is infinite. For small k, you have long wavelength modes. On the other hand, when you look at the optical branch, in the optical branch, we said that successive primitive cells pick up a phase of -1. So what this cell does, Yeah, what this cell does, the next cell would do exactly the opposite. So which one is the which spring here? One has to see, but the point here is that no, sorry. What I'm saying is at k equal to 0. So all the primitive cells do exactly the same thing. So whatever this thing does, this would do exactly the same. So this is again, if this moves this way, this atom would move this way. If this moves this way, this atom would move this way. And what do the atoms in the same cell do? Now for the optical branch, remember, we got epsilon 2 by epsilon 1 to be minus 1. So they would be moving out of phase. So these two atoms, these are in the same cell. This is the K spring. They are moving out of phase. So when this goes this way, this atom in the same cell goes this way. But whatever this cell does exactly the same thing. So these two atoms would do exactly the same thing as these two atoms. So this is the K equal to 0 or long wavelength optical mode. When you go to the zone boundaries, all that changes is that the epsilon 2 by epsilon 1 values are again the same. It is 1 for acoustic branch and minus 1 for optical branch. So for the acoustic branch, two atoms in the same cell would do exactly the same. They would move in phase. Here, they would move in phase. But here they would move in phase in the acoustic branch. And for the acoustic branch, so what we said is that when k is equal to pi over a, you pick up a phase of -1. So whatever this cell does, this cell would be out of phase. So when these two move this way, these two would move that way. When these two move this way, these two would move that way, and so on. When you come to the optical branch, again, two atoms in the same cell would move out of phase because epsilon by 2 by epsilon 1 is -1, and two successive the primitive cells would also be out of phase because there is a factor of -1. So when this goes this way, this would go this way. This one would also go this way. This one would also go that way, and so on. So that's the short wavelength or zone boundary optical mode. So these are the extreme cases. In between case, the motion of the atoms would be look more complex, but there will be a certain periodicity depending on what k value one has. So this relates to the question one of you asked last time. Who was it, Harshit? That what is the, what are these U's? So you see, depending on what k you are talking about, and which mode, which branch you are talking about, the motions are related. There is certain periodicity and there is certain phase relations. Okay, so any questions at this point?
So are we still at absolute zero?
That's a good question. Well, if you treat these things classically, the motion of the ions classically, then they should not move at absolute zero. But in real, if you ask of real life, they don't behave classically. They have quantum nature. So therefore, the 0-point motions are also important. So eventually we'll have to look at quantum treatment of these lattice vibrations. But at this point, yes, we are treating them classically. So therefore, at absolute zero, they wouldn't move. But we are not at absolute zero. So if there is a thermal energy, then they would move and vibrate. And these are the sort of types of vibration. So these are the normal modes of their vibrations.
Okay, sir.
Mm-hmm. Well, if there are other questions, you can ask. Else, we will meet on Tuesday for the exam. So it's same time, is it? Or would you prefer some other time?